Get started. We will not wait because this week is a special week. Oh, I'm okay. If some people just left the school and for home, I'm totally fine. Okay, it's a Thanksgiving holiday.
Will you grade quiz on Canvas?
Please, yeah,
Yeah,
I agree. Yeah,
it doesn't seem on my Canvas. There's grades in grades.
the grade is on Canvas. Okay, I'm double checking. Is is quiz on Canvas or no?
It's not showing.
Yeah, maybe I just graded on the PDF.
Yeah.
Yeah, I graded already.
We can not see on Canvas.
Yeah, I did not because you emailed me.
Mhm.
So this is a quiz for the modeling and also for the Excel sheet and PDF files. You emailed me instead of uploading them to the cameras. That's the reason. Yeah. So good. For the quiz, I give 100 out of 100 for you guys. You have done good job. Huh? Today we continue our talk. We continue our talk. The last time we talked about the JR curve, the testing, and today we talk about for the calculated J and how to calculate J for the unstable fracture. Last time we talked about for this stable fracture. Today we talk about unstable fracture. Unstable fracture. Here is what is unstable fracture? It means the so previous one. We have previous one and the J testing standards, and they are used for materials that exhibit double crack extension and a rising resistance curve. Double crack extension means that we usually have this is blunting. This is blunting of this crack, shallow crack, and then this crack grows. The rising, the R resistance is rising. Right? So this is double. This is a characteristic of double crack extension. For this is ASTME 1820, but this one, okay. And so also that one also covers the tests that terminate in a unstandard fracture event. So such as cleavage in the stills. So either the basic or resistance, the curve test procedure may be applied to materials that exhibit unstable the fracture. We can use a basic and resistance curve. And resistance curve, we need to use the resistance curve. We need to continuously monitor the crack growth. And for this is basic procedure. And last time I told you what's the difference between the basic procedure and the resistance, the curve procedure. The basic procedure, and you need to monotonically load the specimen to fracture or to a particular displacement depending on the material and behavior. However, for the R, this is for the curve, and for this resistance curve, you need to continuously monitor the crack growth during the test. This is the difference between this direct procedure, basic procedure, and the resistance curve procedure. So then we take a look at the value of J as a point of unstable fracture. We are focusing on unstable fracture. It's designated as GQC. Right? So this is different from our previous designation. So this is a provisional fracture toughness. If certain validity criteria are met, and certain validity criteria are met, and we just let this GQC to be the GC, the critical one. So there are several validity criteria, and so this needs to be satisfied. First one, specimen size requirement, right? The specimen size requirement. I'm going to, you need to know these details. First, the B value, B is the thickness. The capital B is the thickness. And the P0, what is the P0, guys?
Initial ligament.
Huh?
The initial ligament length.
Yes, yes. Or lowercase P0 is the initial, P is ligament length. P0 is the initial one at the very beginning. So if these two values, they are greater than the lambda GQZ, GQZ is what you just got. And sigma y, and what is the sigma y, guys? Last time I asked you guys, sigma y here is a flow stress. It is the average of yield strength and the ultimate strength, right? I told you guys, right? Be very, very careful of sigma y. Lambda is the dimensionless constant. If the material is a ferritic steel with a tensile property within a certain range, you can use the lambda equal 50. Otherwise, you just use lambda equals 100. So this is the first validity criterion. Second one, validity criterion for the GC is a maximum allowable stable crack prior to stable fracture. So this is delta A cannot be higher than 0.2 millimeter plus GQ divided by M sigma y. Again, sigma y is a flow stress. It equals is a constant, material constant. It is half of the yield strength of this material, and this is plus this is the average of yield strength, and this is ultimate strength. M is a value, okay? M is slope of the blunting line, unless the blunting line slope has been experimentally determined for the material. M is normally assumed to be 2.0. So it is 2.0. You can use this one. So these two validity criteria need to be checked. So the size requirement for GC is intended to ensure that the specimen has sufficient crack-tape triaxiality, okay? And that further increases in size will not significantly affect triaxiality. However, GC value may still exhibit specimen size dependency. So this is be very, very careful. The sensitivity of GU, the GU is another this designation. GU here means the J value at a fracture instability. Okay, when the fracture instability occurs, this value is called GU. This GU to specimen size has not been fully quantified. Consequently, ASTM warns that such value may be size independent. So this means that this ASTM protocols is not perfect. Okay, it's not perfect. And for the unstable fracture, so this is J. We calculate this J, but sometimes this J value is size dependent, specimen size dependent. If this is the case, you need to be very, very careful. So this is reason that when you do the experiment, if your experimental results is kind of different from other people's results or other people's results in the literature, and don't be confused, okay? Don't be astonished. So this is section 7.43 and talk about critical J value for unstable fracture. Then look at next one is CTOD testing. And we know that CTOD is another important characteristic parameter to characterize the fracture. Okay, CTOD. The first CTOD test standard was published in Great Britain in 1979. So after that, so this is ASTM, so American the Society of Testing on the Material, and they proposed a protocol named 1290. And so this one has experienced several revisions. You can see based on the technology advancement and these people in this community will continuously perfect. This is the protocol. ASTME 8020 is the old friends. We have talked about this one multiple times. This one combines the stress intensity factor and J integral and CTOD into a single testing standard. The CTOD test method in E1290 and E8020 are similar, but the later one includes provisions for generating a CTOD resistance curve. And now, because of this, we focus on the ASTM E8020 test method. Because this guy have some standards for generating a CTOD resistance curve. So ASTM E8020 includes both the basic and resistance curve procedure for CTOD, much like the J-test methodology in this standard. And you guys know what is the basic procedure and the resistance curve procedure, right? I told you guys several times. What is the basic procedure? Basic procedure means that you monotonically load the specimen until it fills or until a predefined displacement. So second one, resistance curve procedure means that you need to monitor the crack length periodically. So this can give you a lot of the work you need to do. You need to know that, okay? I might ask you, this is the conceptual knowledge. If you do not pay attention to what I say in the final exam, and you might be confused. If you are confused, you will be frustrated, and then you will be angry with me. Okay. But now this is what I'm talking. Okay. Basic procedure, stable crack growth is not considered for here. So for the experimental CTOD estimates, and we use this one. We use this delta is total CTOD, and we decompose this guy into two parts. One is the elastic part, one is the plastic part. So elastic part can be obtained using this equation. And so because we know the delta CTOD has a relationship with the stress intensity factor, and for this equation, K is the stress intensity factor. This nu is Poisson's ratio, and sigma ys here is the yield strength, and E is Young's modulus. And how to calculate the K? And we have this equation, okay? We have this equation, P is the applied load, and B is the thickness, and this W is the width of your specimen, and then multiply by polynomial in terms of the ratio of crack length and to the specimen's width. So this one delta EI is easy to get. We can get this delta EI analytically and using that equation. But this delta EI assumes that dn, dn is dimensionless factor equals 0.5 for linear elastic material. So when we just record the equation 3-14, the delta equals dnj divided by sigma 0. So this is what we have learned in the equation 3.18. For this one, for plastic part, we will follow this one. This is a hinge, and so this is 3-point bending. So these are two support points. So we apply load, and here is a gauge, and to measure the distance between these two tapes. Okay, and so we focusing on two different specimens. Where one is called this is the single edge notched is a specimen, bending specimen, SENB. Second one is the compact. This is testing. Compact the specimen is a specimen we used for our quiz 1 modeling. Okay, you should know that. So for this is SENB specimen, and we usually have a knife. The two knives. Is the two knives here. and we measure the distance between these two knives. You can see, okay, so delta PL is obtained by assuming that the test specimen rotates about a plastic hinge. And we suppose this is a plastic hinge. We rotate about it. You get that figure. Delta PL, okay, we can use the similarity between this is the two triangles. Delta PL here, okay? Delta PL, and this is delta PL can be obtained using this equation. And you can see delta PL is usually difficult to measure directly, okay? You understand this? But in experiments, we cannot measure delta P directly. And what can be easily measured? VP. You can see VP is outside. Is outside. That is distance between two knives. The tips of two knives. It's very easy to measure. But luckily, we know the similarity between these two triangles. These two triangles, I told you several times. If we draw a vertical line, so this triangle, right, will be similar to this triangle. So based on the similarity of these two red triangles, and we can derive delta PL, and once we have the value VP, which can be measured directly. Right? Understand? So sometimes my students, they are confused. We here and we do not measure the delta directly. We measure the VP directly. So VP here, crack mouse measured with a clip gauge. And VP is obtained as in figure 3.6. So that is the figure is very similar to this one. So RP, plastic rotational factor, it belongs to 0 and 1. It determines relative position of the apparent hinge point. So how to determine the hinge point? And you need to do some tests to determine the RP, to determine the hinge point, the point here. How to do that? And look at the ASTM 1820. Okay, it shows given the geometry of the specimen and how to get this is a hinge point. So actually, this is very interesting. And if we had, I wish we had this is the experiments, instrumentation equipment that we can do these tests. So for SEB is single edge. This is bending this one, okay? Specimen, and Z there is a Z value, and Z is a knife height, okay? The knife height. And when we have a knife, because for this guy it's difficult to measure from here to here. However, for compact specimen, and Z equals 0. But for SEB, RP equals 0.44, okay? So for compact, so this is an equation we need to follow to calculate RP. As I said, RP is the position of the hinge point. And you need to look at these two equations. So these two equations are given in the ASTM 1820. But now I'm giving you now, okay? That's good? So whenever you want to do experiments, you have got to follow some protocol. And these protocols, they are standardized, and everybody needs to follow. And then you can compare your results with other people's results. And here RP is a polynomial in terms of the ratio of initial crack length and to the initial ligament length. So B0 is initial ligament length. Okay, so here is one way to calculate the VP. Determination of plastic component of the crack mouth open displacement. We go this way, going down, and then really remove this is the loading and go back So this one will be your VP. And we call residual displacement. Residual displacement means the plastic deformation after you fully remove the loading condition, and you still, the displacement still experiences some displacement. As I said, this figure is comparable or equivalent and to the one that I show you sigma and epsilon the diagram. Okay? So questions regarding this slide? No question? So when you use the resistance curve, but here up to now we talk about and we monotonically load the condition and to load this specimen and to calculate the delta. However, if we use the resistance curve procedure, which means that we need to monitor the crack length continuously. If you use this procedure, the CTOD equation must continuously be updated with the current crack size. And for the ice measurement, for the mass measurement point in the test. And so this is on how we calculate this is a CTOD. So you can see when we compare this equation with this equation, this one, okay, this one plus this, and we will find that so they are similar, but we add another iteration, another variable i. I is the iteration index. That means which iteration you are talking about, or which measurement. We continuously we should not call the iteration. We just call the step. Where's the S step? AI is the current crack length, and you are interested. And delta AI is a crack growth equals the current AI minus this is the original AI. This is the crack length. The stress intensity factor Ki is computed using the current crack length. Keep in mind, I is here is the S step. So for compact specimen, the rotational factor must also be continuously updated. So this equation, okay? So this equation and this equation, that equation is from this equation. So here. Questions so far? Because a compact specimen, for this compact specimen, the RP is dependent upon the A0 and B0. So you need to update RP also because your crack length is growing, right? However, for the ICEB, RP is constant. For the ICEB, you do not need to update your RP, which always equal to 0.44. That's the reason. And here, you need to update RPI as well. Questions? Okay. When the material exhibits ductile crack extension, that means the blanking and also the plastic deformation, the above procedure can be used to generate a delta R curve. We have delta R curve, the R is rising. The CTOD near the onset of the ductile crack extension, we designated it as delta IC, can be inferred from the resistance curve in a manner very similar to TIC measurement I see in figure 7.24. So 7.24, I showed you guys, is a curve. We have one line, and we have another line, and then we have a horizontal line. Within this is the four lines, all the data, and we just best fit it, right? So that procedure you need to be very, very careful, because I told you guys I might test you. The slope of the blunting line and exclusion lines for delta R curve is we call it MT, where MT I'm sorry, I'm delta, okay, delta is assumed to be 1.4 unless experimentally obtained measurement of Brownian line slope is available. So you can just assume this guy equals 1.4 if you do not have your own experimental measurement. So the provisional initiation toughness delta Q is defined as the intersection between delta R curve defined by a power law fit within the exclusion. So this is exactly what I show you in figure 7.24, right? The several steps. And a 0.2 millimeter offset line with a slope of mt. The size requirement for valid delta IC is given by this, and you need to check if this inequality is satisfied and this delta IC is valid. Otherwise, then you need to redo. You need to increase the specimen size to redo. Okay? So this one using this one to check. The basic, however, for another procedure, the basic procedure can be used to measure delta IC, but multiple specimens are required to define a delta R curve. Why? Because the basic procedure, we will monotonically load the specimen until it fills or until to a predefined displacement. And so we do not measure the crack length continuously. So it should be noted that ASTM E1290 does not provide a procedure to measure delta IC. Be very careful. That's the reason we prefer to use ASTM E1280, 1820. So for tests that terminate in unstable fracture, for example, cleavage in ferritic, the symbols delta C and delta U are assigned to the resulting CTOD values, guys. We know delta C means critical. What is delta U, guys? Right? So this delta U is the delta U. We talk about the JU. The JU. We talk about the JU here. The JU means the J value at the fracture instability, and delta U is also here is designated as the CTOD value at the fracture instability. Can I write down, guys? Delta U here is analogous to the JU, and whenever you see the subscript is U, it means that this is the value at fracture instability. JU and delta U, whenever you see this is subscript, it means at fracture instability. What? So don't be confused. We have JC and delta C, and then we have JU delta U. Don't be confused. So as you can see, the property symbol depends on whether or not the fracture's instability was preceded by significant stable crack extension, as in the case with JC and JU measurement in ASTM. JC is comparable with delta C, and JU is analogous to the delta U. But be very careful. So, when assessing the toughness in accordance to ASTM E8020, here are two case scenarios. First one is if the crack growth for this step is less than 0.2 millimeter plus delta QU and divided by M delta. So you can use delta U, right? However, if delta A is less than 0.2 plus delta QU divided by M delta. And this is the protocol imposes the following set requirements. So you must check if this one works or not. If this one works, okay. Otherwise, so this is delta U cannot be used. Questions so far? You can see there are a lot of inequality we call inequalities that we need to follow to check and if this is obtained values are valid or not. So this size requirement is approximately 2 or 4 times more stringent than the requirement on the GC. Right? And look at this equation on 7.19. It is likely that a future revision of ASTM 8020 will relax the CTOD size requirement to make it consistent with the TC size requirement. So in ASTM E1290, so this is 1290, and the fracture instability toughness is designated as delta U if delta A is greater than 0.2 millimeter. So that is a different protocol, right? So when applying the basic test method to a ductile material that does not exhibit fracture instability. Fracture instability means that suddenly the crack growth is very huge and is out of control and will until the whole specimen fails. That's a fracture instability. It is usually not possible to infer a delta R curve or delta IC, but the value of CTOD as a max load plateau delta M can be obtained. So this is maximum load point is the result of competition between strain hardening, which causes the load to increase with the deformation, right? Because the crack is growing also, and the ductile crack growth, which reduces the cross section of the specimen. So look at these 3 curves: fracture A, B, and C. We can see the difference between them. The CTOD at the maximum loading in a ductile material gives a relative indication of toughness. However, delta M is highly dependent upon this specimen size. So this is delta M. Right? This is a PM and corresponding delta M. For this figure, a series of schematic load displacement curve that illustrates a variety of failure scenarios. For first curve, you can see here, on the first curve, at this point, it fractures. For the first curve, illustrate a test that results in a delta C value is critical. Right? At this point, our target point, it fractures. Unstable fracture occurs at PC. After here, it goes down. Fracture. So figure 7.29b for this one, right? Is a fracture occurs at this PU, this PI. Correspond to a delta U result where ductile terrain persists unstable fracture. Ductile terrain. So ductile, we have before this guy fractures, we have the strain hardening, right? So this is a ductile terrain, just pull it. The ductile crack growth initiates at the PI. So ductile growth at this PI, the ductile growth initiates at this point and then go until it finally the break. A test on a fully ductile material produced a load displacement curve from C in which max load plateau occurs at the PI. It goes this way. Right? So you can see. So these 3 types of CTOD results, delta C, delta U, and delta M, they are mutually exclusive. That is, they cannot occur in the same test. So you can see either any of them, but you cannot see both any combination of them because these three case scenarios they are competing to each other. They cannot coexist in the same test. Okay, and today we have talked about and how to calculate the J value for unstable fracture and CTOD testing. And this is the so we talk about the ASTM 8020 as ATM ASTM 1290. There's a lot of equations here, but I don't ask you guys to memorize. And however, you guys need to know how to use this is the procedure, these equations, and to do the tests and how to validate your test results. Okay. So up to now, we have finished, and all this is the testing, so experimental parts related to the fracture mechanics. And from next class, and we are going to teach, this is a fatigue, the fatigue problem, how to handle the fatigue, what is the fatigue, and how to handle the fatigue. Any questions for me? No question? Okay, if there's no question, I'm going to end today's session. And I hope everyone of you guys have a wonderful and safe exam period. Bye.